Formal verification gives provable guarantee of the correctness of programs and eliminates classes of bugs and vulnerabilities in system software. To verify the correctness of a loop invariant is needed. A loop invariant is a formula that holds true before and after each iteration of the loop. Consider this simple example. This loop calculates the cube of A, but to verify it indeed correctly calculates the cube of A, we need such a loop invariant. This work proposes a method to automatically find these invariants, and we focus on nonlinear invariants, which is more challenging. Our system GCLN first run the source program for many different times using different initial states, and then we get execution traces. Then from the execution traces, we build such a neural model, a CLN model, to learn candidate invariants. And then we use the Z3 SMT solver to check if the candidate invariant is indeed correct. If not, we use the counterexample to enlarge sampling and do the steps again. I can only give a very high-level idea of our many techniques in this paper. In this first step of collecting execution traces, in some cases where the normal traces is not enough, we use fractional sampling to collect more traces, more fine-grained traces. And in cases where the inequality invariant is difficult to learn, for example, here we have n smaller than or equal to a, we propose a new activation function to learn tight inequalities, for example, this solid red line here. And to effectively learn logical connections, for example, the AND here or somewhere, we proposed gated T-norm and gated T-conorm, which can basically turn on and off the logical connections. And finally, the core of our neural model, continuous logic networks, is basically a parametric relaxation of SMT formulas. So traditionally, such a Boolean formula should only be calculated to 0 or 1, and we relax its semantics and get values between 0 and 1. Please read our paper if you want to learn more about automatically learning loop invariants.